So welcome everybody to this symposium on the mathematics of neuroscience, technology and engineering, normally held in Rhodes, but this year virtually. And since it's virtual, we thought we'd send out this welcome and introductory video so that everybody starts at the same stage, independent of their time zones. This is Dan and I last year, running the conference from Lindos, which is a city on Rhodes. Last year was virtual. This year it's been wonderful to be able to hold it again in spite of the pandemic. But next year we really hope to hold physical participation. And we invite everybody who submitted this year to apply again. You'll find that the island of Rhodes is a very conducive place for exploratory and in-depth thinking. So this is a symposium on the mathematics of neuroscience, not only two seemingly different disciplines, but also perhaps disparate philosophies. And indeed, this debate begins with the Greeks, where, as so beautifully illustrated by Raphael in his School of Athens, Plato points up, explaining reality by reference to a world of abstract forms and ideals. And Aristotle gestures down, explaining knowledge in terms of experiences and examples. In this conference, as in that debate, we also seek to reconcile the worlds of mathematics and neuroscience. In a simple sense, the need to do so is clear. As we accrue more observations and data on the brain, quantitative methods are increasingly necessary to manage that data and relate them to our scientific theories. But there is an unquestionable sense in which a mathematical analysis of the brain has the potential to move us towards a deeper understanding of the challenges it overcomes with grace. Exploratory thought and ideas that address both of these aspects are the aim of this symposium and well embodied in all the submissions we've seen so far. Incidentally, this is a good way to introduce ourselves, with Dan, the elder, coming from a background in mathematics, and myself, the younger, coming from a background in the neurosciences. We met at graduate medical school in Oxford and have been working together ever since to combine our interests in this area. So the question is, how are we to reconcile these two worlds? How are we to structure our analysis and progress? Well, one way to start is to think about one thought experiment. Imagine we've landed on an alien planet and we've found this black box. It's covered in a set of buttons which can be pressed and also light up, or change in illumination. How are we to investigate this object? What questions can and should we ask of it in order to understand it better? If you'd like to pause the video and come up with some of your own, please feel free to do so. What you tend to find when conducting this thought experiment in a classroom setting is that there is a great deal of overlap in the questions people propose. Here on the image is a sample of those. For example, what is it made out of? What happens if we press these different combinations, and how long does it take to respond? Is it emitting anything? Can we scan it? There is also a different type of question people tend to ask that seem to center on the role of the object. For example, where did we find it, in what context, and who uses it? Now, a simple but extremely helpful observation made by the theoretical neuroscientist David Marr was that these questions can be grouped by the type of explanation a satisfactory answer would require. For our black box example, we can see that we have a number of why questions, for which a sensible answer requires a statement of a purpose or function, a set of how questions at a different explanatory level, for which a mechanistic answer seems the most satisfactory, and a set of what questions that are aimed at a physical description. Marr famously used these levels of analysis to construct a framework for answering questions about any information processing device. It is this framework that I believe presents the most useful and consistent way to relate mathematics to neuroscience. At the most abstract, we have the computational level, in which why questions can be answered by considering the computational goal or task of the device or agent, and arriving at a logic for the strategy by which any ideal learner could carry it out. This goal is justified in turn by its relevance to the wider environment, as well as external norms and cultures. Notice here that the considerations arise from the environment, objective and ideal behavior of any agent, and have very little at all to do with what is happening inside its head. The next level is the algorithmic level, in which how questions can be answered by proposing a representation for the input and output, and an algorithm for making that transformation. And finally, there is the implementation level, which consists of analysis as to the actual physical constitution or implementation of the proposed algorithm, whether in vivo or in silico. In order to explore this approach a little more concretely, let's consider a toy problem first, a cash register at a checkout. So the computational goal of this register is fairly straightforward, or perhaps even including the person operating it, to assist with exchanging goods for money or vice versa. And now we could formulate a set of requirements that we intuitively expect of any solution to such a goal. This arises from consideration of what it is people are doing in the shopping environment and what they are led to expect by society. So for example, a few things that come to mind are that buying nothing should cost nothing, that the order of items is unimportant. The grouping of those items is also unimportant. And if you buy something and take it back, you should have a net zero cost. Now, you might see that these requirements actually specify the formal system of addition. We are then free to use what we know from this formal system as a logic to give the optimal and consistent solution to this kind of computational problem. That doesn't say anything about what exactly is going inside the cash machine's head, but it does give us a great deal of information what a satisfactory solution has to look like. At the algorithmic level, we have to specify how we are to represent these numbers and an algorithm that can transform these representations based on the functionality required. Obviously, how we represent those inputs and outputs has a great deal of influence on which algorithms we can and want to choose. One thing to note here is that on this level, we have a problem of identifiability. An infinitude of algorithmic solutions can compute a given function based on the input and output. This is why neuroscience explanations given only at this level tend to feel unsatisfactory. How are we to know that they are in fact right, or compare them to theories based on another research group? But it's also the level at which we seem naturally to seek an explanation or find one satisfying. This is how it actually does something, or instructions or actions for changing things in the real world. Finally, we have the implementation level. This is a physical mechanism capable of implementing the known or inferred algorithm that the device is running. Clearly, some implementations will work better for some algorithms and vice versa. It's also the level of data discovery, where experimental results from neuroscience, a field where we still know very little of the total physical goings on, can greatly affect our understanding or challenge us to develop new areas of mathematics to account for brain data. So Ma didn't mean that any of these levels were better than each other, rather the opposite, that gaining a deep understanding of any information processing device would involve satisfactory answers at each of these levels that complemented each other. Said another way, for each level to make sense requires a consideration, even if a loose one, of the constraints imposed by theories or models at these other levels. We've considered a black box and a cash register, but what we are really interested in is the brain. Ma showed that many of the current approaches to neuroscience in the 1980s were misguided because they either involved answering a question at one level with an answer at another, or they didn't take into account these relationships. Okay, enough with toy examples. Let's take a real world example from neuroscience, and that is the field of reinforcement learning. This is a field where analysis is being performed at all three of these levels, and clear links between them have been established. And some people call it the poster child of Ma. So broadly speaking, the computational goal in reinforcement learning is for an agent to maximize reward within an environment. The formal system that most people think appropriate is called a Markov decision process, in which an agent acts on a usually stochastic environment, causing it to change its state and possibly generate a reward. In this setting, an optimal agent will choose the best policy, which action to select when in an environment. This is usually stated as maximizing the expected future reward under a time decay factor. There are many choices for how to represent these environments and goals, as well as how to structure a strategy. This is the algorithmic level development of analysis. The main choice here is that given the computational level goal, what are the most efficient ways to find or approximate the optimal solution? The main distinction we've seen in research is between using model-based strategies, in which an agent builds an explicit model of the transition matrix and reward function, and model-free strategies, where an agent optimizes over local objectives using cheap and approximate computations. Typically, these exploit the Markov property of the environment given in the computational level formalization. And one method that has proven particularly relevant is using the temporal difference between approximations to generate prediction errors, which serve to push the approximation closer to the objective function. Finally, at the physical level, there's a reasonably well worked out circuit in the brain that researchers think implements these goals and algorithms. This consists of neurons in a group of conserved structures in the deeper part of the brain called the basal ganglia. There is strong evidence of prediction errors mediated by the neuromodulated dopamine when animals solve analogous problems in laboratory settings. Although recently, there is emerging evidence from research on this level of analysis that also fits the model-based approach, and particularly in humans. So here we have seen an example of how analysis at each level can help guide a process of scientific investigation and discovery in neuroscience. For a more in-depth review, I've got a paper at the end that you can check out by Yale Nib's lab at Princeton. So taking a step back, the actual content of our theories at each of these levels are themselves mathematical models. Logic and formal systems at the computational level, algorithms, and then biophysics. So clearly there is great potential for mathematical developments in neuroscience. During this symposium, I invite you all to consider which level of analysis your approach is located at and what data you would ideally gather to confirm or disprove it. On the other hand, using this methodology as a scientific hypothesis itself, that it is the best way to seek consistent, meaningful, and implementable knowledge about the brain. You may think there are altogether different methodologies for analysis, and we would love to hear about them. One simple observation is that this framework is a functionalist one, relying on forcing us to think about a learning agent adapting or being optimized to solve problems in an environment. Maybe that's not all there is to the brain or our experience. And of course, the field of neuroscience itself has different scales of investigation at which all levels of analysis can again be considered. And of course, this means considering our mathematical models at each of these levels. And a complete theory of neuroscience might even be thought of all of the connections and all of the mutual constraints between our understanding at each of these scales and levels of analysis. And as what we're relating is our mathematical models, again, there seems to be great potential here for mathematics to influence our overall understanding or theories of the brain. I would like to finish by focusing a little bit more on the computational level, because it's the one that I think offers the most fruitful structure to relate mathematics to neuroscience. So Markin famously said that trying to understand perception by studying only neurons is like trying to understand bird flight by studying only feathers. It just cannot be done. His point is that in order to really understand bird flight and these answers at the algorithmic level and the implementation level, we have to first understand aerodynamics, the problem the bird is overcoming. Only then do the structure of feathers and the different shape of birds' wings make sense. So he also said, there must exist an additional level of understanding at which the character of information processing tasks carried out during perception are analyzed and understood in a way that is independent of the particular mechanisms or structures that implement them in our heads. And this emphasis on the computational level has proven extremely fruitful and interesting in psychological research and is growing in influence in modern machine learning. Of course, we can think about mathematics and neuroscience together here. Mathematics by defining and discovering these formal systems based on our observations of behavioral goals and constraints, arguably exactly what was happening in Princeton with Nash and the development of game theory, so beautifully portrayed in A Beautiful Mind. But neuroscience has the role of providing those behaviors and constraints, but also challenging formal systems to account for them. And at the end, I'll talk about a book by Douglas Hofstadter that illustrates this approach most beautifully. So I will leave everyone there and I will pass on to Dan. And before doing so, I'd like to thank my PhD supervisor, Tom Griffiths at Princeton, who provided most of this structure or structured thought about analyzing the brain, and also my friend Taylor Beck, who pointed me in the direction of the School of Athens by Raphael, and whose ideas I have elaborated on in the beginning. Thanks to our keynote and invited speakers, and you all for presenting. It's going to be a wonderful conference, and I'm really excited to hear the talks. So for a bit of reading, the first book here on the left by John Anderson is the one that really cashes out this framework of MAR in a beautiful and simple computational manner, and I recommend reading it to anybody who has a little spare time. The second book, I'm a Strange Loop by Douglas Hofstadter, is extremely thought-provoking and demonstrates a couple of these different ways in which he believes that modern mathematics doesn't have the necessary logic to account for really fundamental human behaviors and introspection. At the start, we had an image from Penrose, The Road to Reality, and the book that really put about these series of MAR is called Vision, and this is the Yale NIV paper at the bottom that I talked about during reinforcement learning. Thank you for listening, and we are very excited about the symposium next week, and hope you are too.